Welcome to another Math Research Live with me, Charlotte Aten. I'm happy to see so many people already here today. That's really awesome. Yeah, it should be a pretty cool one today. I've got some announcements before I maybe properly get started. So first of all, well, I hope everyone's doing awesome, had a good week, or starting a good week. Yeah, so I have a couple different things to announce before really getting started. The first of which is that I finally figured out how to have the chat show up in the video. Without further ado, I have the chat showing up here. Well, hopefully. I mean, can people see this? Is this visible to people in the chat? And if you reply, you should hopefully see yourself in the chat in the display here. Let's see. All right. Or is everyone too shy to test it out? Oh, fantastic. Okay. So thank you so much. I actually don't know how to read your name, Allison X. Clevin, but thank you very much. Yeah, so I'm not really sure why there's like a little bit of a black bar underneath the chat and the display here, but we'll figure that out eventually. I don't really want to fiddle around with it right now. But so that's the first thing. So hopefully we should be able to see people's chats in the YouTube video and stuff as well, and that'll make it a little easier to follow along for people following along later. And if anything questionable happens, then I'll just have to use FFmpeg to slice the video and remove that part. But hopefully everyone will be on their best behavior and it'll be fine. Also within the chat here, so I have the archive, the paper on the archive that I'm going to be talking about today pinned. And I wanted to pin 2 messages, but I realized that it wasn't possible. So if you can see this other one here that's showing up, my partner actually also streams on Twitch, and so there's a link here. It's Supernova Art, and so my partner Nova does art, and also while doing some pretty awesome artwork, also talks about various topics like solar punk stuff, feminism, just a whole bunch of different things. I think they are a little more eclectic in their schedule, as perhaps befits an artist, if I can stereotype. But if you happen to be someone who also finds that kind of stuff interesting, you should definitely go check it out. We've been kind of experimenting with live streaming. Both of us, have been experimenting, and who knows, we may even do something together at some point on live stream. We do also sometimes moderate each other's chats as well, so you may see me over there or see them over here from time to time. Okay, cool. So I think that's about it for all the announcements. So as always, remember, just feel free to ask me whatever. This isn't meant to be a 3-hour-long lecture where I just lecture at you the entire time. You can ask me things and tell me things. And within reason, I will try to respond and answer all of your questions, or just respond to whatever's going on. Okay, cool. So, yeah, again, this article is pinned here, and so if I pop over here, then, well, I guess I'll keep a copy of my own Twitch stream up as well, just so that I can have that going on too. Although I suppose what I realized is that I could actually ban someone from within the interface, and then I just had to close the chat and open it again and got rid of it. So that seems good. All right. So here we can see the chat again. Feel free to ask any questions as long as they're appropriate questions. As you can see, I have this multiplayer rock paper scissors paper. Here, let me do this. Now you can see me again. So I have this multiplayer rock paper scissors paper, and I started writing this when I was living in Yosemite National Park for the summer, almost a decade ago now, and it really just came from me wanting to explain to people how, I was really interested in universal algebra, but a lot of my friends were not math people, and so didn't know about that. And I realized that rock, paper, scissors was actually a really good way to explain to people about what I was interested in. And so this led to this whole long involved project, and I ended up writing a whole paper, which you can see here. And again, this is linked in the pinned thing on the chat. And so here, let's see if I can minimize that. So let me see if I can zoom in as well. Oh, or here we go. We have a nice zoom here. This is basically a bunch of universal algebra and combinatorics, and I figured out a lot of things about these games of multiplayer rock, paper, scissors. So, in particular, I was able to, come up with a list of what I thought should be, not the rules for a particular game, but what I thought would constitute a fair game of multiplayer rock, paper, scissors. So, maybe, you might have a different idea of what would be a reasonable multiplayer version of rock, paper, scissors, and there are other ideas out there, but this was me exploring mine. And so, I'm not going to sit here and read the whole paper to you. As you can see, it's 27 pages long, and it's a bit technical. But what I am going to do is kind of, introduce some of the ideas, and again, feel free to ask questions at any time. I'm going to introduce some ideas, and I'm going to work my way up to actually addressing some of these questions that I had left unanswered. Here, let me see if I can get this to pop over a little bit better. Okay, perfect. So if we scroll all the way to the end, maybe just kind of skipping to the very end here. Okay, that was too far, but let's see. Okay, maybe not literally right at the end, but somewhere close to the end here. I have some questions that I believe I left unanswered. Well, maybe I didn't actually state them as a problem, but well, let me see. So I didn't intentionally pre-prepare myself so that you would actually see me re-exploring this since it's been a minute. Okay, so I didn't state these as a question really, but I had some discussion where I kind of left some questions open. I kind of thought I stated them as an actual problem, but maybe I didn't. Let's see. So, as you can see, I've got lots of nice tables. This was my first single author paper that was published, and I was very, very proud of finishing this. It was a long process. Okay. Well, I remember the question that I wanted to answer, so I'll just have to find it. I'll have to find the relevant things in here. But now that you're sufficiently exposed to me scrolling through the paper, maybe I'll start to talk about what this is. Well, maybe I'll use the paper to do this instead of just rewriting some of this stuff from scratch. So, maybe I already went too far past the introduction. The idea is that you can view rock, paper, scissors as actually being a binary operation, kind of like what I was talking about last week. As you'll notice, there are definitely some common themes in my research, and this is one of them. Alright, well actually, okay. Oh, this is big enough. So, this is the rock, paper, scissors operation. And the idea is that each of the things that you're plugging in is like the choice that one of the players makes. And so, maybe the first player chooses paper, and the second player chooses scissors, so you find where that row and that column overlap each other, and it says scissors. So that means if one person chose to do scissors and another person chose to do paper, then scissors would win. And so then that would be the winner. And like here, if both people choose paper, then this is saying that paper wins, and so like that's like saying that it's a tie, you know. So that's it's kind of taking care of the case where there's ties. So one way to think of it is like I'm saying here, like this operation is saying which item wins, and if both people choose the same item, then both people win. It's a tie. So you can think of rock, paper, scissors as actually being a binary operation in this manner. And so, well, similarly, there are some other games that are similar to this. And so, if I scroll down here, there's actually a French variant of rock, paper, scissors, where there's rock, paper, and scissors, and then there's also an item called the well. And I guess it's that the rock loses to the well because it falls into it, and scissors falls into the well. The scissors fall into the well also, I guess, which defeats them somehow. But the paper can cover the well, and that stops it or something. So paper defeats well, and of course it still ties with itself. So that's you know, that's how the well works in relation to the other things. But this game actually isn't really fair in the sense that oh well, as it says right here, there's more ways to win by playing paper than there is by like playing rock. I mean, if you know, if you just look at the number of ways that paper shows up here, it's a lot more often than rock shows up. You only have 3 appearances of rock here, but 5 appearances of paper. So like rock is not a good choice to play in this game. So the French version of rock, paper, scissors isn't really fair. It's not fair to the different items. And so also something that's been in the popular culture is this so-called rock, paper, scissors, Spock lizard. I put a V for Vulcan for Spock, you know, from Star Trek. And so you can see here the rules, you know, are a little bit more complicated. I can't remember it off the top of my head. It's, you know, it's a complicated thing to remember. But maybe later on I'll show you there's kind of an arithmetic trick for remembering this or reproducing this without having to actually memorize the all of which things defeat which other things. But there's a lot of rock, paper, scissors like games out there, and this one I would actually say is fair in the sense that I'm interested in. But you know, a lot of things that you might come up with are not. So you know, it's I'm not just interested in kind of anything that you can do where you choose some items and some rules for which ones beat which other ones. You know. Okay. So. Well, maybe I should just talk a little bit about, you know, kind of the general idea of these things and what they have to do with graph theory or combinatorics. Does anyone have any questions yet? Obviously, you know, I'm not sitting here and like, you know, literally reading the whole paper to you, but if you see something that sparks your curiosity, just let me know, and we'll check it out. Okay, you had a question, but you worked it out. You figured it out. Oh, okay. So when was the last time I played rock, paper, scissors in real life? All right. So this is actually I think this is funny. So like sometimes people will actually like introduce me to other people and be like, oh, this is Charlotte. She does rock, paper, scissors. You know, like that's like I'm the rock, paper, scissors person, right? And so you'd think that I would play rock, paper, scissors or be like competitive for rock, paper, scissors. The funny thing is that I'm actually pretty bad at it. I mean, of course, it's fair in the sense that if you truly choose randomly, you know, and there's no choice that has a better chance than anything else. But I think there's some trick to maybe like reading your opponent or like trying to like see what they're about to do like right as they're making the move, but not not so late that you're cheating exactly, and like there's some like strategy to it outside of the sort of the rules of the game itself. And so I'm actually not very good. I think it has been years, but yeah, I can't specifically recall. No, actually, I was mentioning, my partner does live streaming earlier too. I think that I've done I think I've played rock paper scissors with them before, so it must it must have done that sometime within the last couple of years. But I don't play it very often. And I have played the multiplayer version of rock, paper, scissors, or a multiplayer version of rock, paper, scissors, like I talk about in this paper with people. But I've only done it a couple times. The rules are actually quite involved to write down or remember. So I have computer programs that can do it for you. But still, then it's like a little bit of a thing to like type everything in, and because I don't have like a nice like app for it. I always thought maybe I would at some point, but it's just not like a high priority. Okay, so now I see. That's a fantastic idea. Dagestani Bear, it's a fantastic idea. I need to learn how to write a bot for the Twitch chat is what I need to do. So that's definitely going to be one of my goals going forward, I think, since the bot's useful for many reasons, and one of them is this. So yeah, because like I gave a talk when I was in grad school about this stuff, and I did have a game where I think there were 17 people playing simultaneously, so just one round where 17 people chose something, and we had everyone like secretly write down their choice for like what item to use, and we ended up with we had like I think it was 17 people, and it was 16 grad students in the math department and one neuroscience grad student, and the neuroscience grad student was the unique winner. There was no tie or anything. It was just one person, and it happened to be the one person who was not a math PhD student. So that was pretty amusing. But yeah, I think that's by far the biggest game of multiplayer rock paper scissors that I've ever played. But yeah, I mean, I already have some code, so I can definitely put something in the chat. That's easier than writing like an Android application or something, because like, writing the application, you've got to like do all the graphics, which, again, maybe my partner's the person for that, but we got to do all the graphics, and then you've got to get it posted on the on the App Store and everything. Oh yeah, definitely. The neuroscience grad student definitely had some kind of advantage that I don't know what it was, but yeah, there was some kind of mental trickery at play for sure. Oh, I see. Okay, so you had a conversation about a version where you submit an algorithm, which takes as input the opponent's algorithm, and you try to read their mind. This actually kind of reminds me of there's like so people who study game theory, or who study games, will sometimes describe games as actually being that like your strategy, or like what one player's strategy is like how a complete description of how you would respond to any other thing that your opponent did, and similarly that's your opponent's strategy. So I'm not sure if it's 100% the same thing as what you're saying, but it's definitely in a very similar vein. This is a thing that people actually do. So yeah, it's definitely something that people do in game theory. Of course, I guess there's a little bit of asymmetry here. If I guess maybe someone has to go. Well, okay, I see. Like both people choose their algorithms, but like, are you saying would you plug your algorithm into your opponent's, and your opponent would plug their algorithm into yours, or like how or does it just go like one way? Because like that's maybe not symmetric in the same way that rock paper scissors usually is. But I mean, it's still a neat idea either way. Okay. Well. Oh, I see. Um, okay, so the conclusion is okay. Yeah. Yeah, I guess if you give a non-halting algorithm, then you can just kind of, yeah, you can just force a tie. So you definitely can't lose, but you definitely can't win either. Okay, so do you go 1 2 1 2 3 and then go, or 1 2 3 shoot and then go? Um, uh, hmm. I think I've always done. I think I've always done like on shoot, like rock paper scissors shoot, and then you choose your item at that moment that you say it. I think that's how it's supposed to go. If I recall correctly. I don't explicitly describe that in the paper, but I mean it should be obvious, of course, that's the right way to do it. Um, yeah, so maybe I'll actually describe kind of the connection that this ended up having to abstract algebra and to combinatorics, assuming there are. Oh, yeah, I should have cited the paper where people proved that was the correct thing. Absolutely. Yeah, let me see. I'm still kind of feeling like I can find here where I talk about what the connection that this has to an open problem. Let's see. Yeah, so I guess I didn't really state it as a problem. In my more recent papers, I'll actually have something that's bold, like how there's like lemma, theorem, whatever. I'll actually have something that says like a problem that we're not going to actually answer in the paper, but that's just something that you might try to do on your own. And I found where such a thing is in here, or maybe it does appear like that in the final published paper. I don't remember, but this is pretty similar anyway. So here I said that I get some kind of bound, and I said it helps us search for identities. And so what I'll maybe try to explain a little bit more as I go forward is that like there was this problem which was mostly really answered back in the late 90s about whether the what's called the variety of tournament algebras, and I'll tell you a little bit about what that is. Whether the variety of tournament algebras is finitely based, and it turned out that it was not. And you don't say infinitely based because it's either finitely based or it's not finitely based. Because you can, as I'll maybe mentioned in some amount of detail, you can always find an infinite basis for a variety. So like it's not really interesting. And it's not a basis in the sense of linear algebra exactly. So it's kind of a somewhat philosophically similar notion, but I'll mention what it is. But there was this question, and it was basically answered. It was basically answered in the late 90s, and the answer was it's not finitely based, and so that was kind of the end of a lot of interest in it really, because that was basically the resolution. But there was this remaining question, which was, well, okay, so this variety is not finitely based, but can we still find an interesting, like describable basis for it that's infinite? And in my paper, I make some progress possibly towards doing that. I don't actually do that exactly, but my results in this paper could probably be used to do that. And since I've never really sat down and tried to use my results in order to do that, I want to show you what it would look like if I started to try to do that, just having not looked at this in a long time. And I'll tell you from the outset, just because this type of thing generally might not be the easiest thing in the world, that it's unlikely that I will completely be able to answer the problem in the next 2.5 hours. But I will try, in addition to answering your questions and talking about whatever comes up. I will try, and you will get to see what it looks like for me to just start on something like this that I haven't been already preparing for. It's just something I've thought off and on for a while. Maybe it's possible to answer this question, and now I'm going to show what it looks like if I try to do that. Don't maybe you'll be blown away by the fact that I know all of the stuff about this paper already, but don't expect to be totally blown away by my attempt to answer this question in the time allotted, because this type of thing usually takes some time, and especially because I intentionally didn't really prepare myself at all beforehand. You're going to really just watch whatever the first steps are of me doing this thing. Which is going to be a lot of me refiguring out what it is that I did before, and so I hope that this is interesting. Although it's a little bit disappointing in a certain way, because it's like when you actually see the reality of it, you're like, that's actually doesn't seem as maybe as wild as I thought that it was going to be. So maybe that's cool in one way, because it's pretty attainable actually, but it's maybe in another way it's like, real life is actually maybe not as wild as what you might have imagined. Let's see. Rock doesn't beat paper. Let me try to draw this correctly. So the first step of all this stuff, I'm going to actually give you some kind of introduction to what any of this really has to do with algebra. The first step in all this stuff is to say, if we look at rock, paper, and make sure I don't go too far over, and scissors, then paper beats rock because paper covers rock, and that defeats it somehow. Rock beats scissors because I guess you can destroy scissors with a rock. And then scissors beats paper because I guess cutting paper is defeating paper. So you have this directed graph like this, where there's an arrow pointing from each thing to the thing that it defeats. So rock beats scissors, scissors beats paper, paper beats rock. So the way that we can see this as being a binary operation is that if we, I already had this table in the paper before, but if you look at paper and rock, the winner between paper and rock is whatever has the arrow coming out of it. So the arrow will be pointing from paper to rock, so paper beats rock. So paper goes here and here. Have I thought about the correspondence between magmas and binary relations by something like less than or equal to being saying that f of a b equals a? Actually, I'm happy to report to you that I know exactly what those are. So maybe let me take a little bit of an aside and talk about what happens with some other binary relation that's not this rock paper scissors one, and then I'll come back and I'll finish doing that. So I'm happy to report to you that I can answer your question here in quite a bit of detail, and there are good answers to it. So first of all, if I just choose some set, I usually call it A because it's the first letter of the alphabet, I guess. Maybe secretly because my last name is Aten, and so it's also the first letter of my last name, but don't tell anyone. Can anyone else do the video? Am I still moving around doing stuff? Okay. Let's see. It doesn't seem frozen for me. Oh, okay. All right. So it is working for other people. Hopefully your connection will stabilize in a minute then. Thanks for the confirmation. so let's say that my set A has like, maybe I'll just do little a, little b. Oh, good. Ah, it's fixed. Nice. So I'll do little a, little b, and little c. And let's say that my relation, binary relation R, just pretend that is the letter R. Let's say that my relation R has ordered pairs like AB, maybe BC. Why not? Well, okay, if we literally just did what I just described here, this kind of looks like maybe it's something that you could think of as less than or equal to, because it's like saying A is less than B and B is less than C. However, if you just if you just do this and define the binary operation the way that you were saying, so that like maybe saying like if x, if xy is, if a pair of things is in the relation R, then that means that the product, or f of xy equals, say, x. Well, if we did that and we wrote out a table for this, we'd have ABC, ABC, and then we have A and B, so A times B would be A, and then B times C would be B, but that wouldn't actually really define the entire rest of the table. So this wouldn't really be a binary operation in the sense that it would be undefined for lots of values. And so, as you point out, the rock, paper, scissors relation isn't transitive, but for other magmas it can be. And so, so the idea is, well, okay, in order to get a complete multiplication table, we would need to choose basically an ordering for every pair of elements, and also I guess each element would have to be like less than or equal to itself, or just related to itself according to the relation. So actually, going back up to my rock, paper, scissors example, we kind of want to put loops up here on each of the things. So rock defeats rock, paper defeats paper, and scissors defeats scissors. So okay, so we need not just a binary relation, but one that has like exactly one out of AB or BA for every like possible pair of things like that. We either have to have BC or we have to have CB. And so if you think about what it would mean to have a relation like that, let's say I finish this one. I'll complete this one to an actual relation that actually works for giving us a binary operation. So we'll have AB, BC, I'll do AC, and then I'll do AA, BB, and CC. Okay. So now if I do this, then what's going to happen is that my relation R actually will tell me how to fill in all of these spots uniquely, which is also important. Oh, yeah, I could say f of AB equals A if A is related to B, otherwise f of AB equals B. But that's kind of like, effectively it has about the same information, right? Because if it has to be one or the other, then I can just know, okay, if AB is not in my relation, if A is not less than or equal to B, then I'll just say that, B is less than or equal to A, basically. So, I mean, you can, but it's kind of equivalent to what I'm doing here, if that makes sense. So, like, if I did do this relation where I added this stuff in, then you'd end up getting this kind of table. So let's say, let's see. Right, f of AB will just be A. So f of AB is A, so f of BC is B, f of AC, f of AC is, oh, right, I see, that's actually, that's, okay, I see what you're saying now, right, so it means f of xy is in R means f of xy is equal to x, and also f of yx is equal to x. Right, otherwise I'd still have some pairs undefined. I see what you're saying now. Yeah, I do I do need to add that as well. I was just missing that. I see what you're saying. Yeah. So we do need that in order to get an actual binary operation where it's defined for all of the different orderings. Okay, so here now, because AB is in our relation, we also know that f of BA is A. Okay. And then similarly, we think of this as being like, oh, kind of like A is less than or equal to C. So so we get this, and then if you fill the rest of it out, you'll see that you get that. So it looks like this. And so now there's a couple different ways you can think about this. So maybe I'll just pop down here a little bit before returning to the rock, paper, scissors example. So if you do this, there's a couple ways to think about it. The first way is to say that, well, it's actually still like we have a graph whose vertices are A, B, and C, and we have an arrow pointing from, from one to the other when, I guess we'll say that maybe A defeats B because it's less than or equal to it in the like if we're doing the rock, paper, scissors example from before, so maybe there should be an arrow from A to B and an arrow from B to C. But now things look different from the rock, paper, scissors example because there's also an arrow from A to C, not the other way around. So it's not like cyclic. It doesn't just go in a cycle. And then each of the nodes has a loop that goes back to itself. Okay. And so you'll notice that if you choose any relation that works for this, in the sense that you can define a binary operation the way that I have here from the relation, then basically what you're doing is you're taking a, so this is an example, and the previous graph was also an example of what's called a tournament. Yeah, you're right. Okay, so yeah, I was taking a little bit longer to explain it, but you remembered correctly. So what you were asking for is equivalent to commutative semigroup. It's a binary operation which is associative, idempotent, or idempotent on some set, and you can always give. Sorry. It's not total order though. It's partial order. So the example that we're talking about in this one is it's a total order, but it doesn't have to be. So here, let me show you an example that comes from a partial order instead. Here, I'll do a new page. So if you want to see an example of such a thing that comes from a partial order, take the same underlying set, A, B, C, and take a relation where we say that A is less than B, A is less than C, and then put in the diagonal. Oh, okay. Well, okay. I guess I should say that this is a little bit different from our previous example because okay. So yeah. All right. I see. Okay. So it's not that every commutative semigroup is the minimum function for some total order. So there is an example of. I guess I'll just say it this way. There's an example of a commutative semigroup that comes from a partial order. That is not, it's not one of these tournament ones that, like, up here we were able to put basically an arrow between every two things, and that's the same up here, and so those are giving us what are called tournaments. But you can choose a partial order on a set that gives you an operation in the kind of like the way that you were thinking about with the minimum. So like in this case, it would be like A lies below B, and A lies below C, but B and C are incomparable. It's not true that B is not below C, C is not below B, they're just two different things and they're incomparable. And so you can think of this as a semigroup where you can say, you can say, well, basically, you know, you can define like f, you know, I guess instead of a, b, I'll say x, y. You can define f of x, y as being, here, I'll just kind of also write this in English. The largest member of A below x and y with respect to the partial order. Oh, I guess I'm not saying that this is a set. It's the specific element, not a set. It's just, yeah. It's the largest member. It's the largest member of the set below x and y with respect to the partial order. This is also known as the meet of x and y, like MEET, like they're meeting each other. So this would be the meet. Okay, and confusingly, and this is just a part of life, just like how there's all sorts of weird things about English or whatever your favorite human language is. But in mathematical language, which is also human, but it's not, I guess I would say not a natural language exactly, because, you know, it's kind of manufactured more. But for some reason, we write the meet like this, even though, like, B meet C is equal to A in this semilattice, or commutative semigroup. Even though it looks like the opposite picture for some unfathomable reason, and now we're not going to change it because it's been too long, and we just have to live with it. Yeah. But anyway, that's the meet. But of course, the distinction is kind of meaningless when you're only talking about a single operation, because I could view this whole thing as a join semilattice instead if I just turn it upside down. Yeah, Boolean algebra is something that is a meet semilattice and a join semilattice at the same time, and there's a certain kind of compatibility between the meet and the join, and you also have a complement that's like not. Yeah, so this is indeed the same exact kind of thing. It's the same, you know. It's this is slightly more general or slightly more abstract, but yeah, this is definitely the same type of thing that you've seen if you've seen Boolean algebras before. So yeah, that's absolutely what it is. So this one doesn't really come from a tournament like the other ones did, but it still comes from some partial order, or poset if you prefer. Alright, I guess does that answer the, okay, does this kind of answer the question about, you know, defining operations from relations, like, in maybe in more generality? Seems good. I guess you said it works, so it works for you. So like probably that means that that you're cool with this. But just let me know if there's anything else that you're wondering about, or anything else like that. But yeah. So what I was interested in this paper though was oh, well, yeah, I guess it wasn't a specific question, but I'm glad that I was able to share my ideas on that. You also can go off in other directions, like you can say, okay, well, maybe I can't define an operation from just any relation, but maybe I can define a partial operation where I just leave some of the products undefined. It's not really a true operation, but it's like a partially defined one. There's other directions you can go with it, but yeah, maybe I'll just leave it at that for now. But what I was interested in this paper, so there are examples where, like this tournament, tournament, or this magma, it's actually a commutative semigroup, and it comes from the partial order that says like A lies below B and B lies below C. If you want to think of it as a meet semilattice, so this actually happens to give, you know, what we might call a meet semilattice. Or in other words, it's an associative binary operation, which is also idempotent. So, you know, just maybe to remind people, associative means, you know, if you do x and then times y times z, you get the same thing as xy times z. And idempotent, which might be a little bit newer, or idempotent, just means if you multiply anything with itself, you just get back the same thing. That's what a semilattice is. And formally, there's really no difference between a meet semilattice and a join semilattice. They're just semilattices. Because if you had one of them, you could always view it as the other kind by just flipping the picture upside down. You just take the diagram, this kind of diagram here, that was a sad circle, but this kind of diagram here, or similarly, this kind of diagram here. These are called Hasse diagrams. Maybe I'll just do this. This is called the Hasse diagram for a posat. It's just a way of showing which things are less than or equal to each other, and as you would imagine, the things that are below, like A is below B because it's lower than B in the picture and it has an arrow going up to it, but B is not below C and C is not below B. They're just unrelated. So, yeah. So on the other hand, these first examples I was doing, this one, and also this one that wasn't transitive, so it's not a partial order. This one coming from the rock, paper, scissors operation, which I guess I'll finish filling out now, right? So there's an arrow going from rock to scissors, so rock beats scissors, and then there's an arrow going from scissors to paper, so scissors beats paper. We still get a binary operation, but the ordering is not transitive. You know, there's not like, you can't, you know, rock is below paper and paper is below scissors. Rock is below scissors and scissors is below paper, but that doesn't mean that rock is below paper. It's the other way around. So this isn't a partial order. It's kind of a cyclic order that just goes around, but we still get a binary operation out of it. And so this is also an example of what I would call a tournament algebra. So this graph over here is a tournament. This graph over here is also a tournament. In general, tournament graph is one where you take some nodes. You can have more than 3, but I'll just start off with 3 because it gets really tedious to draw all of the nodes in the graph. And then just put all possible edges between them and also give them loops. Oh, if the spider plays 4 simultaneously, okay, yeah, 4 simultaneous matches with itself. I see, like each pair of spider hands are doing one of the matches. Is that single player or multiplayer? Well, so actually, I would consider that to be a 2-player game in a way. That is actually, I don't know if this is at all what you were getting towards, but I was actually going to mention at some point during the stream, we can do what's called the product of these algebras or of these magmas, and what you're describing is actually like the product of the sort of like the fourfold product of the rock paper scissors magma with itself. So that's actually a very relevant algebraic construction for the problem that I wanted to try to think about. There's a lot of interesting stuff which I'm not a neuroscientist or a psychologist or anything, but there's a lot of interesting stuff with the split brain phenomena and like conditions where like sometimes people's like conscious perception is damaged, but their unconscious perception isn't. So there's people who have like blind sight and stuff where like they if you like throw a ball at them, they can like defend themselves. Like they'll be like, something's being thrown at me. But if you ask them why they did that, they'll tell you that they don't know and that they just like can't. They just felt like they needed to do that, and like it's true, like they really can't like read or find their way around in like any like conventional way. it's possible for all sorts of really interesting things like that to happen. I mean, of course, it's also quite sad, when people have something that's can make life more challenging, but it's interesting from a medical perspective, because it helps us to understand the brain better. Even okay, this isn't at all on the same level, but even I have some of this going on because I've never been able to smell anything. So it might have just been that I got a virus when I was very, very young, like too young to remember, that ruined my sense of smell, like how COVID did with a lot of people's. But it's also possible that something did not form normally in my brain, and smell just doesn't work for me. Just like how sometimes people are born blind, and that's just what it is. So yeah, it's maybe not quite as interesting, but it's maybe interesting to think about. Wow, what is the part of my brain whose job it is to smell things doing if it's not smelling things? And one possible answer is maybe that it's doing math, or maybe it's just useless, or maybe my brain does process smells in some sense, but it cannot reach my conscious awareness. I don't know about that last one though, because even if like something, it doesn't matter how strong something is. Like if there's like garbage or something, like the room will be cleared, but I will not perceive it. So I think that I'm not unconsciously aware of it either. Anyway, maybe I'll tell you a tournament graph. So what is this kind of graph that I want to think about? Just take the graph where you have all of your nodes, however many nodes you want, and you put edges going between every possible pair of nodes and also each node with itself, just undirected. Then choose a direction for each of the edges. Like here, maybe I'll choose this one to go up here, this one to go up here. Maybe I'll give them names. I'll call this A, I'll call this B, I'll call this C. And then maybe I'll have an arrow going here to here. And then there's really no choice for the arrows that are just going from each node to itself. And then whatever orientation you choose on each of the edges to make it into a directed graph, that gives you a multiplication. So A times A is A, B times C is B, C times C is C. And then, well, let's see. It looks like C defeats A, if we're thinking of it that way. So if we do C and A, we'll get C. B defeats A as well, so if we do B and A, we'll get B. And then C defeats B, so if we do C, okay. Alright, okay, so I guess I just happened to choose the one that I did before. There's not so many possibilities when there's only 3 nodes. But the point is you could do this for a larger number of nodes. You could say like, okay, maybe I'll take 4. I'll do 4 once just to show you that it's possible to do it with more nodes. I have to connect every possible pair of vertices together, including this way and also this way. And I have to do loops on all the vertices, and then I have to give an orientation to each of the loops. Oh, yeah. So. Well, I guess I want conservative and commutative. So yeah, tournament. So this would be the tournament on the left. This would be the corresponding tournament magma or tournament algebra. Oh, if I could spell tournament correctly, that would be nice as well. Tournament magma. And so, yeah. So conservative. So tournaments are basically the same thing as conservative, commutative magmas. So if I choose some orientation on these edges, I'll call them A, B. Call the vertices A, B, C, and D. Maybe we have A to B, B to C, D to C, D to A to C, and B to D. Why not? If we do that, then we'll get some binary operation. And as you'll notice, as you'll notice when we define the corresponding binary operation, the corresponding tournament magma, to make it into an algebraic thing, then, well, because of the loops, we're just always going to have that this diagonal is like this, and because this is always like this, anything times itself is itself. So all of these are going to be, well, here, I guess I'll just say it like this. Like, because we always have this is exactly what it means for this operation to be idempotent. Idempotent just means like making itself, creating itself, and so it's like saying like x times x is always just equal to x. So we're always going to have that for our tournament magmas, but then they can look quite different for the rest of the operation. So for instance, let's see, A defeats B if we're thinking of it that way. So should have an A here and an A here. And then, let's see, B defeats C. So, oh, that's A and C. I need to do B and C, so B defeats C. And let's see, A defeats C, so if I do A and C, I'll get A. And then D defeats A. And then, let's see, D, let's see, B defeats D, so B and D, we get B. And then, let's see, C, D defeats C, so we've got that. Okay. So, this one is not transitive, so it's not just coming from one of those semilattices or those commutative idempotent semi-groups, because I believe I saw something that didn't follow the rule here. Oh yeah, so D defeats A defeats B, but D doesn't defeat B. B defeats D. So actually, A, B, and D, if you just look at those three, that's like a copy of the rock, paper, scissors operation. It's like a copy of the rock, paper, scissors thing inside of here. And that's a pretty common feature that you will find in these. Yeah, so in addition to being idempotent, these are also commutative. Like, in other words, if you do x times y, you're always going to get the same thing as if you do y times x, just kind of from the way that we defined it. If you'll notice, whenever I filled in like this one, I'd fill in the corresponding one that was mirrored over here. A times c is always the same thing as c times a, and so on and so forth. Oh, and of course, CA are also my initials, so I made a good choice. Yeah, so we have that it's idempotent, x times x is x. We have that it's commutative, x times y is y times x. And, well, we also have that it's conservative. So what conservative means in this context is that either x times y is equal to x, or x times y is equal to y, just for any particular choice of x and y. In other words, another way that you can say this is that x times y belongs to the set, oh, I was going to write A, but belongs to the set that consists of x and y. It has to be one of those. So in other words, if you combine two things, you've got to get one of the two things that you chose. Rock and paper can't play against each other and then have scissors win. That doesn't make any sense. It can't be that everyone loses. There can be a tie, but it can't be that just everyone loses. It's not very fun. Yeah. So okay. So then there's a little bit more to it, but basically for multiplayer versions of rock paper scissors, I said, okay, I want some operation that takes three or more things and combines them together so that it's like idempotent. You know, if everyone chooses the same thing, it's a tie. The order doesn't really matter, so it's like commutative. The order of which, who's player 1 and player 2 and so forth, it doesn't matter. You just get the same. Thing either way. And then I also want that it's conservative so that like at least one of the people has to win. Like it would be really unfun if everyone could choose their thing and then there's no winner. Like ties are okay, but just having everyone lose is kind of is just not really very amusing. And so that's basically, in other words, I wanted to generalize this notion of tournament algebra. So you start off with something like a tournament graph, and then you get the corresponding algebra from it. So, so there's a kind of natural question that came up like really early on in people studying tournament algebras. As you might imagine, people have studied these things for like forever, for a very long time. Let's see, page after. So people have looked at tournament algebras for a long time, and so just for tournament magmas, forgetting the multiplayer part for now. So just for tournament magmas, well, you know, they're, as I said, they're idempotent. You know, x times x is always equal to x. They're commutative. X times y is equal to y times x, and they're also conservative. They kind of conserve their inputs. X times y has to be a member of x and y. It has to be one or the other. And so, so the thing that's natural to ask is can I come up with a list of axioms like this that will describe all of the algebraic structures I could make by combining tournament magmas together? And I'll explain what that means, unless there are any other questions about anything else, and then I'll explain that also, or answer whatever you're curious about. Yeah, so don't forget, you know, you don't have to just let me lecture at you. I will happily answer any reasonable question that you have. If your question is like prove the Riemann hypothesis, I'm not gonna be doing that. But not because I don't know the proof, of course. Everyone is really you know in the know does, but you're not supposed to tell people. No, I'm just kidding. I don't know that. Yeah, so my goal was to show my friends like what kind of, you know, what universal algebra was about, and I did that by so I'm playing around with some class of algebras. I mean, just kind of showing them that there was a type of multiplication for rock paper scissors, and then figuring out how to make a fair rule set for three people, and being like, that's a multiplication of three things together. In some sense, that was you know, that was as much as I did as far as like showing my friends multiplayer, you know, or showing my friends like kind of the basic idea of universal algebra. But I also was hoping today to try to talk about how there was this problem. This is actually related to this problem that was, you know, in some sense is still unsolved. There, as I mentioned before, there was kind of some answer to this question that I wanted to think about, but it was not maybe the final answer on it, and my paper got a little bit closer to possibly answering it. And so I thought I'd show you what it looked like when I actually try to start answering a question like that. You know, if there's time. Does that make sense? Okay. Or if you want, do people want to see what the 3-player version of rock paper scissors was that I came up with first? Are people curious about that? Or do you want to just hear it? Do you want to just hear what the abstract thing was that was going on in tournament magmas? I'm happy to do both, and I have enough time to do both. Okay. So we have one vote for combining tournaments. Okay. All right. Great. People think that sounds sick. So fantastic. Thank you. So maybe I'll just reproduce rock paper scissors down here. Okay. Here's rock paper scissors. It's rock paper scissors. That R is way too long. Okay, so rock defeats scissors. Scissors defeats paper. Paper defeats rock. Okay. So, so we can think about actually combining two copies of rock, paper, scissors together at a time. And so I'm drawing this X here to mean that this is actually what's called the product, or sometimes Cartesian product, or also known as the or direct product or categorical product or whatever. There's a way to multiply the multiplication rules together, and it's actually not as, it maybe sounds like it's going to be like some some technical thing, but it's actually quite natural, especially in the sense of the spider playing the rock paper scissors game with itself, which is a really good. Oh, I need rock up there, not scissors. Yeah, so I'll definitely be stealing the spider playing rock, paper, scissors with itself when I'm teaching algebra classes in the future, because that's really good. So thank you very much for having pointed that out. I literally never thought about telling the story that way. So you can think about making a new kind of algebraic structure. Okay, maybe I'm going to erase the words Cartesian product here so I can have more room. You can think about making a new kind of algebraic structure where what you do is you think of okay, the spider, I'm going to just do 2 instead of 4. The spider takes 2 pairs of its hands and it plays 2 games of rock, paper, scissors with itself at the same time. And what we'll do is we'll just keep track of what happens in each of the simultaneous games that it plays. We'll just keep track of them separately, but we'll think of them as being happening at the same time. And so the way that I can represent that, assuming that I made enough room for myself, the way that we can represent that is like this. I'll say that the elements, or the basic things for my new algebra, are pairs of things from the old one. So, maybe rock and rock, rock and paper, rock and scissors. Okay, I'm not going to have enough room, but maybe I'll just do dots and hopefully it'll make sense. Paper and rock, the order does matter. Paper, and I guess I don't need a comma there. And then I'll just say dot, there's 9 of them, because there's 3 things and 3 things. And then similarly over here we have rock, rock, paper, rock, scissors, paper, rock, paper, paper, scissors, and 3 other ones, blah, blah, blah. And then the way that we do the multiplication is we just say, like if I want to find out what rock, paper, and rock, scissors are together, then maybe I'll just go over to this spot. Then what I do is I just do rock and rock in the first coordinate, and I'll do paper and scissors in the second coordinate. And so this actually just becomes, here, I'm just going to write what the result is here. Rock and rock is rock, because that's what it is in the first thing. And paper and scissors, let's see, scissors beats paper, so that's scissors. So I should just have rock and scissors in that spot. In other words, it's just like saying, okay, the spider's two of the spider's left hands, right? There's like a first one and a second one. The spider's left hands choose rock and scissors, or rock and paper. The spider's right hands choose rock and scissors. And then, rock wins for the left hands, and scissors wins for the right hands, or whatever. Or I guess for the first pair, rock wins, and for the second pair, scissors wins. So that's what I want to say. Oh, and that's an excellent point. This isn't a tournament anymore. When we do this, we won't have a tournament anymore. It's not going to be. It's not going to give us a tournament. Yeah. So that's a good point. One way to see that is, well, okay. In this case, we actually have that okay, this one, it turns out like it still looks like it's conservative. But let's do like rock, scissors, and maybe paper, rock. Let's see. So if I do rock and paper, no, that's a bad example. Maybe I'll choose a different one. Let's see. What do I want to use? Let's see. So oh, rock, paper, and oh, okay, thank you. Yeah, I was making it harder than I needed to. Yeah, rock, paper, and paper, rock. Good. So if I just go one over, so I'll do rock, paper, and then paper, rock. Well, okay, paper beats rock, so we get paper in the first one, but paper also beats rock, so we get paper in the second one. So I got paper, paper out, but that means that this isn't conservative anymore, because I multiplied two things, rock, paper, and paper, rock, and I got something which wasn't either of those two things, so it's not conservative. So what's going on? Well, we certainly can always get a magma. We can always get some kind of algebraic structure by doing this process of taking this Cartesian product or this direct product of any two magmas. You can just do this with any two magmas, tournament or otherwise. You can do this and you can make a new magma. It's the product magma. So magmas themselves actually have a multiplication operation on them. But when we do this, we see that we don't get something that's conservative anymore. We started with two conservative things, but this isn't conservative. However, this is, as one can check, this is still idempotent, and it also is still commutative. But it's not, in general, this is not going to be conservative anymore. So the fact that if you take two idempotent magmas and you take their product and you get something that's idempotent, that's actually pretty straightforward to see, because if I take like xy and I multiply it by xy, which is the same thing in the product magma, then I'm always going to get xx, yy, because that's how I'm supposed to do the multiplication in the product magma, but x times x is x and y times y is y if the originals are idempotent, so this is still going to be idempotent. Just give it a check mark. Similarly, if what you had originally was, if both of the things originally were commutative, like xy and zw, they don't even have to be the same anymore, well, this is going to be xz, yw, and zx, wy. But that's actually the same thing as zw times xy. So in the product thing, you're still going to have it's still commutative. I'll do another check mark. So taking the product, if two things are idempotent, you get an idempotent one. If two things are commutative, you get a commutative one. But it doesn't work for conservativity. And actually, kind of the reason for that is because, maybe if I go back up here, because being commutative and idempotent were expressible by formulas like this. These are called identities. Like they're what are called universally quantified equations. Yeah, conservativity is not conserved by taking products of magmas. That's just an unfortunate fact of life. So these are saying if these formulas are true for all elements of our algebras, these formulas, if they're true for like the first magma and the second magma, they're going to be true for the product. And the explanation of that is just literally this calculation. This one for the idempotent property, this one for the commutative property. And there's nothing special. There's nothing really special about idempotent or commutative. If you take any kind of formula like that, like even if I took some wild formula, which may not be true for these algebras, but even if I take some wild formula, like I have like x times y times z times x times xz if that's always equal to x times times. I skipped all the way back. Okay, let me see if I can. Let me see if I can get back there. Okay, x times y times times z. Maybe just that random identity that I chose. If I choose two magmas that have this property, like maybe I choose A and B to be two different magmas that each have this property, whatever this bizarre looking identity is. The product here, maybe I'll call this epsilon for equation. If epsilon is this identity, if epsilon is this thing right here, this whole formula, it's basically this will satisfy that formula. That will always be true. This will satisfy epsilon whenever A has that epsilon is true, and so does B. So, in other words, taking products preserves identities. It preserves formulas like this. If you have a formula like this, it's always true. It doesn't matter what the formula is. It's just any random formula. It'll always be preserved by taking products. That's just always going to happen. And again, the verification of that is basically what these calculations are I did here. I'm just kind of doing the property in each of the coordinates at the same time. And so, even if you wanted to do it with like some other random property like this, it would just be basically the same calculation. It would just be longer, like it would just be a more involved expression because this expression is more complicated. But if you could find two magmas that satisfied this property, then you would always find that their product has to also satisfy this property. And it's not really any, other than writing down more tedious, or magma arithmetic, it's not any harder than doing this proof. Yeah. So products preserve identities, but because being conservative is not something that's expressible by a formula like that, there's this kind of or thing going on. Like if you wanted to write it in formal logic, it's like things like idempotence look like saying like for all x, for every possible choice of x, then x times x equals x. So this is an example of what's called universally quantified equation or identity. This is also known as an identity. This universal may also be the universal in universal algebra, depending on your perspective. And so are things like, the commutative properties, like for all x, y, x times y is equal to y times x. It's another universally quantified equation. Those are sort of very good for us in terms of taking products. Something that is not like that is the conservative property, which says it does start off for all x and y, but then it doesn't just have an equation between two expressions like this. It says either x times y is equal to x, or y times x is equal to, or x times y is equal to y. And so because of this, the fact that this or is here, this is not a universally quantified equation. It's kind of, maybe it's close somehow, but it's not it's not a universally quantified equation. So it doesn't play as nice with products. Oh, is there a notion of sums instead of products? Happily, the answer is yes. There is a notion of sums instead of products. There is an abstract explanation of how actually sums and products for algebraic structures like magmas are actually what's called dual to each other. If I did a little bit of category theory, I could show you how actually sums and products are kind of like the same thing but flipped. and I think that's pretty neat. But maybe instead of doing that right off the bat, because it's pretty abstract, I'll yeah. So I can show you the category theory if there's enough interest. But maybe first I should just show you what does the sum of rock paper scissors with itself look like, because that might be more interesting, or maybe not more interesting, but it's better to see an example first. Seeing an example is a lot more helpful than just seeing the abstract nonsense right away. I like the abstract nonsense, but if you haven't seen an example, then it's going to be hard. So let me show you the sum of the two games. So what I did before was the product, and so yeah, what I did before was the product, and that was like saying that that you were playing two games at the same time, and just keeping track of them both as one game, like as if it was a single game. But how do we add rock, paper, scissors to itself? Well, first of all, I'm going to actually getting better at writing down the table without thinking about it now that I'm doing it. Oh no, I did it wrong. I got too overconfident. I started doing the wrong thing. Oh no, because rock beats scissors. Yeah, no, good. Okay, so I want to compute what I really may call this plus this in the abstract algebra sense, or I want to show you what that looks like. And I would do another copy of the table here. The problem is that I actually want to use different symbols for the second copy, and it'll be clear when I do the example why I want to use different symbols for the second copy. So I'm still going to do rock, paper, scissors, but I'm going to call the ones in the second copy A, B, and C, but I'm just going to relabel them all. So what was rock will now be A, what was paper will now be B, and what was scissors will now be C. Okay, that will make my life easier. So here's what the sum of the two games looks like. I'm going to need a lot of space. I'm not going to tediously fill out the whole table. I'm going to explain to you the idea and then leave it at that. Oh hey, hello. Someone just popped in. I'm showing how to add together two copies of the game rock, paper, scissors. These two algebraic structures. I'm showing how to add them together, how to combine them together. Yeah, so stick around if you want to see. Yeah, I think it'll be neat. We previously did the product. So actually, in some sense, multiplication turned out to be a little bit easier, because multiplying them really was kind of like just saying, we'll think of two, like as if it's like two pairs of people each playing their own game of rock, paper, scissors, and our new single game is really just playing the two games separately but at the same time. So that was actually a little bit easier to describe. The sum is something a little bit different. And so the idea for the sum is that, we want something that has both the original, so this is actually going to be, so somehow the winner is going to be determined by these, but there's not really an addition in the sense of adding numbers together. This is more like addition on the actual whole structures themselves. Like I'm adding this whole thing plus this whole thing somehow. So this is kind of at a one higher level of abstraction. And as I mentioned, I'll explain. You'll see how it's related to the multiplication. Does the answer involve an arbitrary choice between the left or the right? No, it doesn't. So it has one copy of rock, paper, scissors inside of it, and so I'll just put that down here. So it has the original rock, paper, scissors inside of it, And it also has the thing on the right inside of it, which is why I wanted to give them different letters. Because if I made the same letters, I would get confused as to which were the left hand rock, paper, scissors and which were the right hand rock, paper, scissors. So now we also have A, B, and C as elements of the sum. So we're putting them together, and they still multiply amongst themselves the way that you would expect them to. So A times A is A, A times B is B, and so forth. Yeah, now the question is, how do you fill in the off-diagonal part? So the idea is that you want to do it in the most general way that you possibly can, which means that if I want to do rock times A, I'm going to make a new element called rock times A, because there's nothing telling me how to do the multiplication over here. And then if I want to do, then I have a new element, which is rock times A. And maybe I want to do rock times A times rock. Well, there's no rule telling me how to do that, so I'll just put parentheses and say it's rock times A times rock. Oh, but that's a new element, so I better have a new element called rock times A times rock. Oh, but I should really be able to, multiply that with something else, and you might say, okay, well, I really want it to be, idempotent and commutative, so maybe there's some things I should identify, like maybe I should say that this is really, A times rock. So I guess, when I do A times rock, it's really the same thing as rock times A. And, similarly, if I do rock times A times itself, then I get itself. So there's some identifications I have to do, and I also have to keep combining things together in every possible way that I can. So it's not, it's not that the cardinality of the sum is the sum of the cardinalities. That's not how it works for algebraic structures. It's more like this had three generators. This had three things that could be used to make everything else. And this had three generators, three things that could be used to make everything. This now has 6 generators. So, I mean, it is kind of like adding in that sense, because there were, 3 things on the left and 3 things on the right. Now there are 6 things in the new structure that can be used to make everything. But as you can see, you have to keep adding new stuff and making new identifications if you want it to. So the making new identifications is a little more technical. There's actually a different plus for commutative idempotent magmas, which is like what I was describing when I was saying that these should be equal and that rock times A should be, multiplied by itself should give itself again. There's actually a different plus for commutative idempotent magmas than there is for just magmas in general. And so this is where it also starts to get a little bit technical. The product is just going to be the same for whether it's just magmas in general. Yeah. So it looks pretty different, and it does look less elegant. But the categorical description of these things is actually the same, and it's quite straightforward actually. When you go to that level of abstraction, it's just kind of like. The sum of algebraic structures tends to it's like the it's sort of like instead of doing them in parallel, you're combining them, but you're allowing them to multiply elements of one by elements of the other, but it's the laziest possible way, and so that usually results in things that are infinitely big, even if you started off with 2 finite things. I mean, I agree, it's maybe not as pretty. And there is this kind of technicality about, well, there's a different plus for commutative idempotent magmas than there is for just magmas. Or, if you were doing like semilattices, like we were talking about earlier, the magma sum, the magma plus of 2 semilattices is not the same as the semilattice sum of 2 semilattices. So it's, it's going to be different in general. But yeah. Oh yeah, actually, it's not a stupid question. Or are you asking? I mean, it's not going to be stupid either way. But are you asking about using graph theory in finding the sum of two magmas, or are you talking about using graph theory in order to just think about the original rock paper scissors in general? They're both good questions. I'm just curious which one you were thinking of, or maybe something else. I didn't realize what you meant. Just in general. Okay, so I mean, I guess first of all, I'll say at the beginning, and what's in the paper, I was talking about tournament magmas. Oh well, I guess maybe I'll go back up here. So you can take any orientation of the complete graph. Oh yeah, so I can also answer the question that came up about free objects in a minute. That's a good question. So you can take any complete graph with loops and orient each of the edges, so make it have an arrow pointing either one way or the other, and then you can always make a magma out of that. You can always make an algebraic operation out of that by saying, if the arrow points from C to A, then C times A is C, and so forth. And so you can always do that, and there is this strong connection to graphs, but also in the context of taking the product of things, if you want to, you can kind of think of this as a graph type thing where you're saying something like, I'll start off at rock, and if I multiply by, maybe if I multiply by paper, then it'll take me over to paper. And, if I multiply paper by scissors, it'll take me over to scissors. And if I multiply scissors by rock, it'll take me back to rock. But if I multiply rock by A, it'll just take me to rock times A. And then if I multiply rock times A by rock, it'll just take me over to, rock times A, parentheses, times rock. And you could think of it as being like an endless sort of graph in this way if you wanted to. Yeah, so you can think of it that way. And it would just kind of keep going on forever because there's kind of an endless list of things that you could add on here. But it would have the little graphs for rock, paper, scissors, and the other copy of rock, paper, scissors inside of it somewhere. Yeah, so there's a lot of ways that you can use graphs to think about these things. This is actually similar to what in group theory would be called the Cayley graph. Usually that's only used with reference to groups, but that's kind of the relevant type of thing. Yeah, do it lazy, so generate an infinite amount of stuff is related to free objects. Maybe I'll just mention what the connection is. So there's also a notion of a free thing. So if I look at, let me just first of all look at the free magma on, I'll just do the generators rock, paper, scissors, A, B, C. Where these now are, I'm just thinking of as some symbols that I chose that could just as well be anything. So what this looks like is basically the most general way to multiply things from whatever that set of generators was, rock, paper, scissors, A, B, C, in a magma. So it's the most general or most lazy way to do that. And so, if I want to write out what the multiplication table looks like, the multiplication table basically says, alright, I'll start off with rock, paper, scissors, A, B, C, rock, paper, scissors, A, B, C, but instead of having any prescribed multiplication for these things already, I'm just going to say rock times rock, I'm just going to call that rock times rock. It's a new element. rock times rock. So I'm just going to make it a new thing. Rock times paper, I'll just call that rock paper. Rock paper is now a new element of the free magma generated by these things. That's rock paper. And then I can, do whatever multiplications I want. If I want to do rock times rock times paper, if I want to do that one, and multiply any of them, then I'll just say, oh, I'm going to declare that to be a new element, and it'll be rock times rock paper. And I need to put the parentheses. I can't not put the parentheses. And this just is the most general, non-associative multiplication that you can define on these basic elements that you have. In other words, it's just all the lists, the ways that you can multiply them with bracketings to express the non-associative multiplication. That's what the free magma on that set of generators looks like. Do people feel okay about that, at least? Like, that's, I'm not going to I can't fill in the whole table. It would take forever. There's an endless amount of elements, but that's what the free magma looks like. It's the most general, laziest way of doing the multiplication, where every time I have to multiply two things, I just say, this is a new thing, and it's just going to be a new element, and that's what it is. Yeah, exactly. So the sum is actually like the free magma with extra constraints. So you can actually always think of the sum as being like that. So first I'm going to take the free magma, which maybe I'll actually call this like F, and then I'm just going to maybe say this is S for my set of. No, I used S for scissors already. G. I guess I'll use G for my set of generators. So this is FG. This is like the free magma on G. So the sum. So the sum of maybe I'll say A with the big A with the underline under it. Maybe I'll say this is the rock paper scissors magma. The one that had like rock, paper, and scissors. And I'll say B is the other one. The rock, paper, scissors. The same rock, paper, scissors one. But I renamed everything so that I wouldn't get confused. So in other words, let's say that B is the one that has just A, B, and C. Then we can actually express this by saying that if I want to take the sum of A and B, what I can do is I can take that free thing. On those generators G, and then I can what's called quotient or divide or identify things basically. It's more like gluing things together than what you maybe normally think of as division of like numbers. And I'm going to enforce that the relationships that rock times rock is equal to rock, and rock times paper is equal to paper, and all the things for the original rock, paper, scissors, and also like A times A is A, and A times B is B, and all of those things, and that would be the magma sum, or it's also sometimes called coproduct. So it's like the product but backwards somehow. Coproduct of A and B. And then if I wanted to do the like commutative idempotent one instead, the lazy way to get back to commutativity or idempotence is to quotient it again. So it's not that the binary operation isn't defined for those values. It's that we define it in the most lazy, cheap way that we possibly can, and that's by just saying there is a new element, which is the product of those things. We just declare it to be so, and we say that we just name it by whatever the multiplication is that we didn't know how to define before. This is cheating. This is how you cheaply make a thing that combines both of them together. Just the easiest possible way is to say whenever I need to multiply two things and I don't know the answer, I say the new answer is a new number that I made up, and it's the expression that I didn't know how to multiply. So this is very much a mathematician's answer to this question, is like of how do I do this? It's just I'll just declare that I succeeded basically. So this is almost in the vein of the story about how have you ever heard the one about how yeah, so it turns out that if you don't want any properties to be preserved at all, you don't end up with any contradictions. So in other words, what I just described here for the magma sum, there's no constraints because it doesn't have to be associative or anything. If you want to take the sum and get something that's commutative or idempotent, so I really should use a different symbol, but I don't want to introduce that many symbols. If you want to introduce something that has more properties or combine them and still keep the idempotent property, yeah, exactly, yeah, just the product of two numbers, well, it's equal to that product, so I'm done. But if you want to introduce more properties, as was already mentioned, you can kind of just quotient it. You can just quotient it again, or you can think of doing it all in one step and saying, I want the multiplications to work the way that they did originally. But then also, in addition to that, I'm gonna say something like, just for any x times x has to be equal to x. For any x, and then I'm also gonna say like x times y has to be equal to y times x. And so if you force these identifications, so for any x and y, so if you force these identifications, yeah, exactly, got him. If we force these identifications, then you might say, well, wait, what if I try to make two things be commutative, but that forces something else that needs to be that, like, maybe I say, like, okay, rock times rock, times rock times paper. Well, if I force rock and paper to commute, then that means that, like, this has to be rock and paper rock, but that also has to be the same thing as paper rock and rock. And, like, how do I know that I can actually identify enough things together so that I'm done? And it turns out that it's possible. So it takes some kind of argument, but it turns out that it's always possible to keep extending the identification until you are done and you can't glue any more things together. If you keep identifying enough things together to make all of these properties true, you will get some kind of algebraic structure that satisfies the desired properties. Now, that structure can actually... Now, this is what's weird. That structure, in addition to possibly being infinite, can also be smaller than the original two structures. It's possible that you can force everything to collapse and just end up with a single element, or just end up with two elements, or whatever. So there's a little bit of checking here, but it is always possible to do this in a way that is not contradictory. You just have to keep following through all of the rules until you can't possibly apply them anymore. Now, actually seeing what that looks like in a specific case can be quite hard. But it is possible in general. Like, it is theoretically possible in the sense that you can prove that you can always do it if you really have the patience to keep doing it forever. Oh yeah, it is similar to answering questions like find the set of... Okay, I'm going to go off on a little bit of a digression now here. Yeah, it's kind of similar to how, like, let's say, like, oh, find, it's like, oh, it's intelligence test, find the pattern, find the, complete the pattern, and it'll be like, like 2, 37, like, 84, and it'll say, like, what comes next? And the answer is you can make anything, come next. You can make any possible thing that you want to come next. Who wants to choose? Someone choose the next number. What's the next number? Something that I can write down without it taking forever. Just what's the next number? I'll make a sequence. I'll make an infinite sequence that has any number you want as the next number. Does anyone want to choose one? 2. The next thing will be 2. I'll finish this pattern, and I'll even do you one better. So if you've already seen this, you know that it's a cheap trick. But I'll even do you one better. Because instead of just giving you some rule, I'll give you an arithmetic rule that makes this happen. this is how kind of ridiculous these questions are. I can even give you a rule that just uses the laws of arithmetic that expresses this pattern. And here's how I'll do it. Well, I'm going to define for you a polynomial expression that gives you the values that gives you the value of this thing. So, okay. Well, first of all, if I want when I plug in, so 1, say this is the first entry, right? Maybe this is the second entry, this is the third entry, this is the fourth entry, and so on. Well, if I'm going to plug in 1 and I'm going to get 2, you know, one way that I could do that is I could say, you know, if I plug in my number, maybe you know, maybe I want to if I plug in 1, I want to make all the other stuff I want to make all the other stuff go away and then just get 2. So maybe I'll say it this way. So so what I want to do is say, okay, p of 1 should be 2, so I'll do 2, and then I'll think of this as being like 1 minus 1 times other stuff. In other words, I'm going to do like p of n is 2 plus n minus 1 times other stuff. Because then it doesn't matter what the other stuff is. When I plug in 1, I'll just get 2. Okay. So now it's possible to just keep repeating this trick, because then when I plug in 2, I want to get 37, right? So I'll do 2, and then well, I already know I'm going to have 1 minus 1, or I'm going to have n minus 1. Excuse me, but then I'll get 2 minus 1 times other stuff. Okay, so what do I need the other stuff to contain? Well, I already get 2. This is going to give me 1 in this case. And so 2 plus what is going to be 37? It's 35. And so then plus, well, I need this, whatever stuff is over here now, to go away. So I'll say, I'll do 2 minus 2 times other stuff. Alright, great. So now, because 2 minus 2 is 0, so it goes away. So now, I'll do 35 plus n minus 2 times some other stuff. And now, if I plug in 1, it'll kill off this entire part over here, and I'll get 2. If I plug in 2, I'll get 2 plus, and then here I'll get a 2, or sorry, I'll get a 1 times 35, and then this will be 0. So then I'll get 37. And now I can just keep going. You see the pattern, right? Now if I want to get 3, well, okay, I'm going to have 2. 3 minus 1 is going to be 2, and then I'll have 35, and then plus 3 minus 2, which is 1, times some other stuff. And yeah, this is just cheating. Okay, maybe we're satisfied at this point. You probably believe I can just keep iterating this, or you can do this process yourself and say, all right, now I plug in something here, and then I say, I do plus 3 minus 3 times blah blah blah, and you just keep doing this. If you only have a finite amount of data points to fit, you can just iterate this process until you have covered all of the values that you need to cover. And if you expand this out, it's just a polynomial with integer coefficients. Even it's just cheating, and so actually I don't remember. I'm not sure if this ends up with the lowest degree polynomial that you can have that does this. No, because probably not, because because I mean, like when I did it to 2 steps, when I distribute, I'm going to get an n squared. So like in general, if I do it like k steps, I'm going to get n to the k, because I'm going to have to keep multiplying this n. So So I think the degree is just determined by how many points you want to fit with the curve. So like if you try to do this to something that's linear, for instance, that's just like 2, 4, 6, 8, end of the k minus k-1. Okay, I was off by 1. But yeah, so if you just try to keep doing this to something linear like 2, 4, 6, 8, 10, whatever, like you still get a higher degree polynomial, I suppose, and it'll just it's I don't think that this has to give you the best. So that's what it is. It's the lowest that works like in general, in the sense that like you need you need a cubic for 4 points. You need a quadratic for 3 points and so forth. So it's not, for specific examples it'll be quite bad, but in general it's the best that you can do. That's true. I mean, this philosophically this is kind of the same type of thing. There's just a way of completing the polynomial in a lazy way that just fills all the things that you need and doesn't care what it does to anything else, that's definitely in a similar vein. And there are other families, as people have mentioned, there's other families of polynomials as well that can do similar things, which might be better for a given application, but this is also just, I guess, part of my rant is just that this is the silliest kind of question to ask. Usually what they mean is, I have a specific arithmetic pattern in mind, and now if you were smart, like me, then you would think of the same exact pattern that was the one that I came up with. And of course, there's, aside from the fact that there's cheap, silly answers to things like this, it's also just doesn't seem, I mean, I'm not a neuroscientist or anything, but it seems like kind of a flawed reasoning that some people can sit down and say, yes, if other people were smart, they would think like we do because we're very smart. Oh yeah, that's the real answer. Okay, so if we're talking about the real clever answer, it's to look it up on the online encyclopedia of integer sequences. That is a fantastic resource. And they have different tools. There's something called SuperSeeker that even if your sequence isn't in there exactly, if it's something it's shifted, or it's the entries are the pairwise products of two of the other sequences in there, it's fantastic. It has so many great things. There's actually something from this project that I wanted to add there, but I didn't. I never did, and I hope to someday. Actually, maybe let me show. Maybe let me show. Oh, the question writer needs to add enough terms. Yeah, they should just add infinitely many terms. Their listen. I'm not familiar with their listen function actually. What is that? Yeah, maybe another time we can do how to count past infinity and do the ordinal numbers. Oh, okay. Oh, that's nice. They can play the online encyclopedia of integer sequences play sequence on a piano with notes mod 88. Oh, yeah, that's too bad. They should really adjust it for the small sequences. Let me see. Actually, let me. Let's see. That's number of outcomes. Oh, maybe if I just do tournament, maybe tournament will give me what I want. Number of tournament sequences. Maybe I'll say tournament graph. So a king chicken in a tournament graph. Okay, I don't think that's what I want. paradoxical. That's just the number of labeled graphs. Outcomes. Huh. Well, there's a lot of things related to tournaments, but it's not just bringing up the number of tournaments in general. Let's see, was it regular tournaments? I have a note about this on my phone. Oh, it doesn't have playback, it just has, okay. I'm going to see if I can find the note about this on my phone about which sequence. Okay, it's the number of regular tournaments. Alright, so regular tournaments have an additional symmetry to them, but this is what I was thinking of. Okay, so if you look at this page in the encyclopedia, oh yeah, Jim Simons passed away, and he was a big supporter of mathematics. It's too bad. So this is the number of unlabeled regular tournaments, and so you've got this sequence, and I believe, so it says there's a program showing this technique. Burnside's lemma is applied here, can be used in the unlabeled case. Number of outcomes. Okay, that's the number of outcomes. But the thing is, a lot of so I'm not sure if I think it's not just using Burnside's lemma, the thing that I was thinking of. So I found this paper that, like, this is a really common thing if you do math. You'll find, or at least if you do the kinds of math I'm interested in, you'll find that there was a paper that was published somewhere in the Soviet Union back in the 20th century that gives a formula for this. That is an exact formula that is something in terms of roots of unity, and it's nice. But the thing is that I don't speak Russian. And I at this point feel like I should probably learn at least a little bit so that I can read these things better. But I want to actually try translating some amount of the paper first before putting out the formula, because I want to make sure that I actually, that it's correct. And I also don't want to just try to reverse engineer the formula without being able to read the prose around it, because it's going to make it more work than it needs to be. But I do want to put the formula on the encyclopedia because there's no formula listed here, but there is actually a nice formula for this. And so at some point, maybe I should just try to crowdsource this and post this paper in the YouTube video description or something, and just be like, hey, if anyone anyone speaks Russian, wants to try to translate this. I mean, I know it's a lot of work, so I don't really realistically expect someone to do it. And, I can try to use machine learning tools, but I've had a lot of experiences where, the character recognition isn't very good for Cyrillic, for the Russian writing system, and then, you get something maybe, but then the translation's not very good, and, it's just, it's tough. If you want to translate between, French and English, that's one thing, but even Russian is already starting to get a little bit too separated from English in order to have a good translation, especially for math. So I'd almost rather just learn it myself at that point. Exactly. You just sometimes you just have to see what you can read by seeing the diagrams, by seeing the formulas. But I just, for this, I didn't really need that formula for anything that I did in my paper, so I just didn't. I just wrote down a note to myself, literally almost a decade ago at this point, I feel. Well, maybe not, but at least 5 or 6 years ago, and I was like, I should really post this on the encyclopedia, and then I never did. But I still remember it, and maybe I will someday. But yeah, it's just, the other thing that makes it really tough is that if you're trying to trace down references to some of these Soviet papers, the Soviet government, they had all of these regional university systems that they set up, and they really pushed people to publish in like there was always like a publishing like press for each of the like local universities, and so the goal I think was perhaps a laudable one of like creating a more like community based publishing infrastructure and maybe democratizing things a little bit more in some sense, but what ended up happening was that the Soviet Union collapsed and like all of these papers are impossible to find. You need like someone to go to like an actual library somewhere in the former Soviet Union and find the paper for you, and it's hard to do that. So yeah, it's unfortunate. Oh, why does it skip even numbers? Okay, so regular tournaments have to have that everyone wins and loses to the same number of people. So here, maybe I'll go back here. Stop complaining about the Soviet academic infrastructure. I actually, believe it or not, I was actually there just very briefly for the end of the 20th century. I think the Soviet Union stopped existing before I started existing, but I still have some complaints about how their libraries are set up now. All right, so what's the deal with a regular tournament? In a regular tournament, each node wins as often as it loses. Yeah, oh yeah. So like for the usual rock, paper, scissors, this is of course possible because, rock beats scissors and scissors beats paper and paper beats rock, and I just won't do the labels for the loops because it doesn't really affect anything. So everyone wins once and loses once. So this is regular. But even on 3 nodes, it doesn't have to be that way. Maybe you have one where A beats everything, and then maybe B beats C, but yeah, this is not regular. A doesn't even lose any times at all, but it wins twice. And so the thing is, when you have an even number of nodes, you can't have that it's regular. I saw that you said Is there anyone in the chat who either wants to see it or do you want to try thinking about it for a minute and seeing if you can see why you can't do this with an even, you can't have it be balanced like this with an even number of nodes? Or I guess this is what I would also call a balanced tournament. Oh yeah. Yeah, it's weird. It's kind of there's a similar thing in the French version of rock, paper, scissors where there's a well and the paper defeats the well by covering it, because it's like covers it. For the rock, it's like it also covers it. At some point a long time ago, people decided that the paper covering things was how it defeated them. But like, I don't know. It's I don't really. It doesn't really have a very intuitive thing going on, but I don't know. How do people feel about this? Do you want me to leave it for you to try for yourself if you don't already see it? Do you want me to just tell you? You can also just look it up, I suppose. Or if you're watching this later, you can always pause your video and try to figure it out. Okay. Well, actually, I was curious. I think I want to scroll back up in the chat because I feel like I may have missed something at some point. And I try to get to everything, but sometimes there's a lot of things. There was something earlier on. Did I go back too far? Maybe I went back too far. Sorry, I thought I missed something, but no. Oh, was it this? With arbitrary choice comment, you combine an item from the left and the right. You always take the left one. Oh yeah, this was the comment that I was remembering. Yeah, it's Yeah, you want to do it in the most general way possible, I guess is the answer. So you can't make a specific choice. Okay, well, nobody seems to feel really strongly about this, so maybe I'll just leave it. But you can try yourself, and you can figure out why it's not possible to make it balanced with an even number of players. You can do it with any odd number, but with an even number, you can't do it. Yeah. Okay. So. Oh, okay. I guess now. Okay, so now at this point, I did sums and products today of algebraic structures. I did some examples of tournament graphs, tournament algebras. So maybe what I want to ask now, since people seem to be satisfied with the regular tournaments for now, what I want to ask now is, how are people feeling about, like, do you want to see the category explanation for what the products and coproducts are, or products and sums of algebraic structures are, or do you want to see where I was going to go with this was explaining what the sort of the universal algebra question was that was related to these things. I'm really good either way. I have 45 minutes left, so I will be able to do some justice to both of these, I think, but I mean, I won't be able to tell you everything in the whole world in 45 minutes. So I need to figure out how to set up like polls or something in here. That's maybe a thing for me to learn for the future. Who wants to see the more universal algebra thing, or the category thing? What are you more interested in? Can I either explain to you how sums and products of algebraic structures are related, and how to explain what they are in general, or I can tell you about what the question is that I was thinking about related to universal algebra with these ones specifically. Okay, I think we have hearts full of neutrality, maybe? Okay, alright, we have a vote for universal algebra. Alright, so let's not worry about whatever the general, like, categorical definition of these sums and products are. What I want to point out is that, okay, so if we take the product of two of these rock, paper, scissors magmas, we'll get something which is still idempotent and commutative, but it's not conservative. And if you think about it, you might wonder, well, what are all the different kinds of magmas that I could get by taking products of tournament magmas? Certainly when I take the product of two tournament magmas, I don't get another tournament magma. It just doesn't give me another tournament magma. But it still gives me something that's idempotent and commutative. And then I can ask something even a little bit more involved than that. So I can say, well, say if I have two tournament magmas, which I'll just say are like, capital A and capital B, I can make three types of things. I can make products of them. I can do like the product of A and B, or I could even do other things, like I could do A with itself, or A with B, or whatever. Right? I can make products. I can also make what are called subalgebras or submagmas. So I could think of like having, like, if I just do like rock and paper. So so paper beats rock. So this is a subalgebra of the rock, paper, scissors one. Rock, paper, scissors. When I decided to do this project, I consigned myself for the rest of all time to just write this table over and over and over again. You may make similar choices with your own life. There's just certain things that you'll have to draw forever over and over again. So a subalgebra is just basically take a subset, and it has to still be closed under the operation. So like for conservative things, actually, this is very easy to do because if you take any subset, it'll be closed under the operation. But yeah, so this is a subalgebra. So I can either make products of my algebras, I could make subalgebras, I could even make subalgebras of products. Like I could choose like a, maybe I'll just say like some subalgebra of, one of the products, like both, A times B or whatever, And I can also form what are called quotients. Yeah, that one table. Yeah. Well, the nice thing is that I don't need to actually make a command to typeset the whole table for me necessarily, because I can either copy and paste it if I really need it again, or what I did in the rock, paper, scissors paper was then I can just have like a, I can just refer back to that figure, that table, and then in future papers I can just say, yeah, and then you can see what the rock, paper, scissors one is back in my one paper that I wrote in 2020, and you can go look at that if you want to go see the table. So now I don't have to actually write it in LaTeX anymore. But yeah, sometimes you just want to make a new command. Oh, also, for those of you who are getting more into writing LaTeX, you got to make your own package. You got to define your own package. I spent so long at the beginning of my time doing this, copying and pasting the preamble with all the function, the different custom command definitions and package imports over and over again. Don't do that. Just make a single package that is your own custom package that has your own commands. And then there's ways in like any Tech Live or whatever like distribution, LaTeX distribution you have. You can just put a symlink to it in a folder, and then you'll be able to call it from anywhere. It's very nice. Highly recommend. So the third thing is quotients. So we usually write P for products, S for subalgebras, and H for quotients for reasons that I'll explain maybe in a minute. But quotients are basically what I was doing earlier. It's stuff like saying take the rock, paper, scissors multiplication. Let me see if I can put this down here. And that's not correct. Paper, scissors, and then do what I was indicating earlier, identify things together. Maybe I'll say I'm gonna make paper and scissors actually be the same element. I'm gonna force paper and scissors to be the same element, and I'm gonna make a new magma like that. So I still have rock, but my other thing is what. Maybe I'll just call it paper scissors. The new other element is paper scissors. Or does this bother people? Should I give it a different name? What do you think? No, that's probably fine, I guess, huh? Because it's just like gluing them together. So I may have a new element, which is paper scissors. And rock times rock is still rock. Rock times paper scissors. Well, if I do rock times paper or scissors, I get either. If I do rock times paper, I get paper. So that makes it seem like rock times paper scissors should give me paper. Oh, but then if I do rock times scissors, I get rock, so that kind of makes it seem like it should be rock. Oh, so I can't just identify paper and scissors. So maybe here I'll just indicate, I'll do a little sad face here. This doesn't make any sense. So I need to keep identifying more stuff. So if I glue paper and scissors together, unfortunately, I actually have to glue rock together to them as well in order to get something that actually makes sense. And so that's kind of what I meant when that sometimes you need to collapse more things in order to finish identifying things together to do that quotienting process. So we kind of just have a single element, which I'll call rock, paper, scissors, and it multiplies to give itself. So this quotient is actually just has a single thing. So even though we only said we wanted to glue paper and scissors together, we ended up having to glue that together with rock as well. So that's not maybe a very exciting example, but that's an example of a quotient. Or this H also stands for what's known as, yeah, this is definitely, yeah. Once you go far enough, there's numbers don't appear very often, and when they do, they're really quite something. But yeah, this is these are also what are known as homomorphic images. There's kind of a slight technical distinction, but let's not worry about it. Yeah, so there's these three things that we can do, and we can make new algebraic structures. We can take products, we can take subalgebras, we can take quotients, we can take, products of things that are already quotients and look at their subalgebras, and we can just do all of these over and over again and make all sorts of different things. This thing that people were interested in is basically what happens if I do all of this as much as possible and make as many magmas as I can from tournaments whose elements are themselves tournaments. Well, okay, so in some sense, abstract algebra doesn't really care what the elements themselves are. If you just call them A, B, C, D, whatever, it's just as good as calling them anything else. But if you're going to say that you have tournaments whose elements are themselves tournaments, and there has to be some kind of relationship between the tournaments that are the elements and the operation of the magma, then now you might have something more interesting going on. But yeah, just saying that you have tournaments whose elements are themselves tournaments by itself, it's actually not very restrictive. I could just as well replace all of the elements of the rock, paper, scissors one with three different tournament magmas or three different tournaments that I chose, and just say that that's what it is. But that's not really very interesting, right? Like that's just renaming things. So if you mean something more interesting than that, then the question is, what is the relationship between the tournaments that are the elements and the magma operation on the tournaments themselves? So yeah, I don't have a good answer for you at the moment for what would be an interesting version of that, but I'm sure that there are some. I'm not really sure at the moment how you would make that into an interesting question. But it should be possible. I just not sure what you want, because you could say, oh, the magma operation has to be the product or something. Oh, okay. Okay. All right, I'll stop trying to figure out how to turn that into a question that has a less trivial answer than my first guess. Okay, so we can think about saying. Writing proofs is a skill that takes a good amount of practice, because what people don't always emphasize enough, but it's a really important thing, is that it's actually communicating an idea to another human being. Yeah, oops. I remember when oof happened. Those are the days, huh? That was a different time. The before time, back when there was oof. It still exists, but it really just took off at some point. And then for a while things were poggers, but I haven't heard poggers in a while. But I'm not really of the right generation for that, so I'm not an expert. Don't worry, I won't say things like poggers anymore, I promise. Okay, So yeah, but yeah, it's, you know, proofs are really communicating ideas to other people, and so, you know, it's not enough to just, it's not enough to be just technically correct, and you also can't just wave your hands and say, oh, you know, it's pretty much like this. It's a good balance between those. I have to say W and L now. What? I'm not sure. I'm not sure what that is. Is this some slang that I'm not familiar with? Hmm. Okay. Well, yeah, I don't know. So okay. So here's what I want to do. I want to say that just think of T as being just all all possible tournament magmas, like all of them. Okay, there's a whole bunch of them. Um, oh, W is good and L is bad. Fair enough. Win and lose. It's also very much on theme for the tournament graphs, tournament magmas. Um, yeah, thanks thanks for explaining. But yeah, you have to include the chain of thought that actually makes it make sense. Um, it's, you know, it's not enough to just say a bunch of things that are actually true. It's good to explain how they're connected to each other. Right? It's also important not to say too much. And you have to figure out where the balance is between what should be obvious for someone reading the proof, or what is enough to show that you really know the proof. Oh yeah, no, I'm not gonna comment on that particular circumstance at the moment. I think I don't want to get any. I mean, it's not really my area anyway. But like, yeah, it's a whole thing. Um, uh, but but yeah, you know, you've got to communicate it at the right level of detail. Because like sometimes, you know, you know, if people start off writing proofs, a lot of people write way too much. And then it's like, you know, I don't need to read all of this. I believe you that like you can show that, like, you know, something that you're supposed to already know works or something like that. So it's, you know, it's really about communication. Yeah. And so that's also why it can be very useful to have the computer, you know, for like automated theorem provers to generate proofs for you. But in some cases, you're actually interested in the idea that you would use to prove something, and just seeing that there is a sequence of valid logical moves that will get you to it doesn't do anything, or it doesn't do that much for you. It's not that it doesn't do anything, because then you know it's true, but like you just go, but I need to know why it's true. I'm trying to use the idea, not the result itself exactly. And so, yeah, machines have a much harder time giving us the actual idea. Yeah, no. So that's the other really great skill is just being okay. I'm putting the sarcasm tag on now. Just being super arrogant and eliminating all of the explanation of how you arrived at an idea, and then just if anyone complains, then you just say it's obvious and you refuse to explain any further. And if you do this hard enough and you have fancy enough credentials, you may get a lot of people to believe you, even when you don't know what you're talking about. There's all sorts of tricks like that, which really shouldn't be a thing, but you know, it's society, and you know, people want to make their way, and people have egos and stuff. Um, yeah, you're allowed to write sentences in math. I know it's tough. It's tough to get people to write sentences in math. You're allowed to use natural language in mathematics. In fact, it's preferred in many cases. Um, yeah, so I don't have a hard time believing that a literature professor is the one who gave you the good advice about writing proofs. It's not hard to believe. Um, well, yeah, I mean, I think generally it's harder to have the idea than it is to write it down. Sometimes writing it down eloquently or writing it down well can be hard, but yeah, I mean, it's coming up with the chain of thought in the first place is usually the hard part. That's the part that really gives you the dopamine hit of like, yeah, I figured it out, solved it, you know, like I understood. You know, you had your epiphany or whatever. Yeah. So, well, so if you remember, maybe I'll go back to this. If you remember, I was talking about that there's three kinds of things that I can make if I have tournament magmas. I mean, I can have more, you know. I can have A, B, C, whatever. I can have a whole bunch. But I can make products. I can take subalgebras. I can make quotients or homomorphic images. And so, so if you think about all possible tournament magmas, we could think about what would happen if we looked at like what I might call P of T, like all products of different tournament magmas. These will include things that are not themselves tournament magmas anymore. Like if I just look at all possible products of tournament magmas, they'll include things like the example that we saw somewhere back up here. Like, where was it? This thing is not a tournament magma, but it is a product of tournament magmas. So like that's something that would be in P of T, but not just in T itself. And then I could similarly look at H of T, all the quotients of tournament magmas, or I could look at, S of T, all subalgebras of tournament magmas. Although if you think about it a little bit, you'll see that doesn't really get us anything because subalgebras of tournament magmas are just tournament magmas. It's just kind of like forgetting the other part of the graph. So, but you could also think about what happens if I look at subalgebras of products of tournament magmas. Yeah, definitely writing down lists of things that you know are true until you understand it better is often a good strategy, because it has to follow from the things that you know are true. This is also one of those things that it's still hard to really totally automate it, but you only know a finite number of things that you can do at any given time. No matter how abstract it gets, there's only so many moves. In fact, if it gets really abstract, there might be very few moves because you only know a couple things that you can do. And so you should just, if all you have is a hammer, everything looks like a nail, just keep doing those moves over and over and over again to everything that you see. I mean, occasionally you might have a genuinely new idea or insight or something, but a lot of the time you can make a lot of progress that it ends up later feeling very, very profound, and you're like, oh wow, I really get it now. But you were the whole time were just oh, I'm just going to keep doing the same thing that I know how to do to everything. I have my hammer. All I know how to do is, first order logic, whatever. I know a couple theorems, and I'm just going to keep doing that. And you'll get all sorts of places. It's really incredible how, there's just only so many things you can do. So as long as you have confidence enough to try and you don't get discouraged, just keep doing it. You'll get places. I'm not going to say you're going to, be the most, successful mathematician who ever lived, but you'll at least be able to do mathematics. I'm quite sure of it. There's still some skill to it, but if the question is just can you do it at all, the answer is basically always yes, you can. Just keep trying all the things that you know until you don't know any more things to try. So yeah. So, okay, so we have these different sort of operations that we can do to make other magmas from tournament magmas. And so, okay, maybe doing subalgebras of them is not very interesting, but if we do subalgebras of products, maybe we'll get some other things. Let's see. Oh yeah. Yeah. So oftentimes the simplest things are also the most useful. I mean, sometimes there really is certain irreducible complexity in a formula or in some kind of pattern, but it's a lot of the simplest things that you can do are actually the most useful. So that's it's part of that notion of mathematical beauty that there's a lot of beauty in things that are simple and perfect in some sense. So we can keep doing these operations, and you may think, oh, maybe this isn't going to be simple because what if I have homomorphic images of subalgebras of products of subalgebras of homomorphic images of products of like blah blah blah. Like, what if I keep doing this? You know, like, oh, what's that? You know, what's that going to make? Whatever, right? Like, it's a lot of different things that I have to consider. It turns out that if you want to get all the possible algebras that you can get by just applying these things in any order, taking products of subalgebras, of quotients, of whatever, actually, you only need to apply each of them once. This is actually just taking quotients of subalgebras of products of these things is the same thing as just doing this just gives you any magma you can make by using the operations, the H, S, and P operations on the class of tournament algebras. Oh, nice! You found some nice formulas for conservative semi groups. That's cool. Yeah. I don't know if I have anything more to say to you specifically about those identities right now, but those are some nice identities to find. So those are okay, I see. Yeah, so conservative semigroups, not idempotent, but just conservative. Well, okay. So this is surprising. Instead of doing all these different operators over and over again, it turns out any magma that you can make by using the operations H, S, and P, the products, quotients, and subalgebras on the tournament algebras, or actually any class, it doesn't just have to be the tournament ones, you can actually just get it by doing them each once, as long as you do them in the right order, which is this order. Take products, then take subalgebras, then take quotients. Those are all the possible ones you could make by doing any order that you want, no matter how many times you combine them. Oh yeah. I'd love to see the proof that you have that uses those identities. That sounds fun. Is it short enough to post in the chat? You can always shoot me an email as well. So, oh, hey, Dobby. Oh, I'm streaming, by the way.
Is it okay that I breakfast?
Yeah. Oh, not in one message. Yeah, maybe it'd be better to shoot me an email. Okay, so I still have 20 minutes, and before, oh, yeah, okay, yeah, or just post it online at some point. Dobby, yeah. Dobby's finally come to visit us.
Hey, sweetie.
Hey, what's up?
I'm sorry to interrupt your stream. Is it okay if we use the blender at some point,
Oh,
like in a minute?
Can you wait 20 minutes? I'll be done in 20 minutes.
Yeah, sure.
Okay, thank you. Okay, so I have 20 minutes, and I want to at least state to you the question that I wanted to try to think about answering. So you can do these things to make a bunch of magmas from the tournament magmas, but as we saw, you get a lot more stuff. They're not just all tournament magmas, so you can make other stuff. And so the interesting thing is that there's another way of expressing what this class of algebras is. So this is actually, it turns out this is actually the same thing as what's called the variety generated by tournament algebras. So this is what's sometimes called the variety, if I can spell variety correctly, generated by tournament algebras. And this is a thing that people have studied for a long, long time. And it turns out that this is actually the same thing as what I might write as models of the identities. This isn't the identity function, it's another thing that I'll tell you. Models of all the identities that are satisfied by all of the tournament algebras. In other words, all of the things that you can make by taking products, subalgebras, and quotients are the same things that you get if you look at all of the algebras, the models. This is mod for models. All of the models, or all of the algebras that satisfy all of the formulas that are true for all the tournament algebras. That's what the identities of T is. So in other words, this is kind of a surprising. Thing. It follows from one of the first results in universal algebra. So it's called Birkhoff's HSP theorem, or Birkhoff's variety theorem, which basically says, in this context, it basically says all the things that you can make by taking products of algebras and quotients from the tournament algebras, or any class, but I'm just going to say it for the tournament algebras, the same things that you get by looking at the models of the identities for the tournament algebras. In other words, these are the magmas. It's the same as looking at the magmas that satisfy all equations that are true for all tournament magmas. Okay, in other words, this includes things like the fact that x times x is equal to x times y is equal to y times x, and probably other stuff too. So that's not obvious. That shouldn't be obvious. But it turns out that if you look at the magmas that satisfy all possible equations that are true for all tournament magmas, that's the same thing as all the stuff that you get by taking quotients of subalgebras of products of tournament magmas. It's not at all obvious, but that's true. And so there's kind of two ways of understanding this then. Either you can understand this variety generated by tournament magmas as being all of the things that you get by taking products and quotients and so forth, or you can understand it as all the things that are, it's not the same as the tournament magmas, as all tournament magmas full stop, because if you look at this product of the rock, paper, scissors one with itself, this is a product of two tournament magmas, but it's not a tournament magma because it's not conservative. However, basically because of this type of argument that I made here, every single equation that's true about rock, paper, scissors will be true about this thing. So this is a thing that's a product of two tournament magmas, and because of Birkhoff's theorem, actually it has to be something that this satisfies every equation. This has to, because of Birkhoff's theorem, which I'm not going to give you the whole proof right now, because Birkhoff's theorem is true, this has to satisfy every possible equation that is true for all possible tournament magmas. So I'll link Cliff Bergman's book again. He has a good introductory universal algebra book that has a good exposition of the theorem. You can find more abstract, categorical treatments of it and stuff, but Cliff Bergman's book is a good one that doesn't use an unnecessary amount of abstraction just to see the first version of the result. There are fancier, more abstract versions, but Cliff Bergman is a good place to start. And actually, well, okay, let me give you a link in the chat so that I'm not making you wait until I post the YouTube video. Yeah, don't just look it up in NCAT Lab. You won't survive. And also it might even be wrong. Like, I mean, this theorem isn't wrong, but like, people can just edit NCAT Lab like it's like Wikipedia. So like, you can't guarantee. Here, let me find this book again. Yeah, and don't accidentally get George Bergman's book. George Bergman is at Berkeley, and his book is more of a graduate level book. So I would start off with this one unless you really want it to be like more like assuming that you've had like you're ready for graduate algebra or graduate universal algebra. But this one, you don't really need like a 2-semester course in abstract algebra. It's helpful, but like this one by Cliff Bergman, he's retired now, but he was at Iowa State University for many years. This is a great place to start. It's a lot more like undergraduate ring theory or something, so it's definitely very helpful. And I'll post a link to this in the chat and also in the video description for YouTube as well. So yeah, that's a good place to find an exposition, and yeah, so this thing, whatever it is, has to satisfy all of the equations that are true for every single tournament algebra simultaneously, even though it itself is not a tournament magma. It's not one of them because it's not conservative. So people are interested in this variety generated by tournament magmas, which can be described in either of these ways. And so a natural question is, is there a short list of identities, if I could spell the word identities correctly, is there a short list of identities or equations so that, here, maybe I'll call the list L. Is there a short list of equations so that the variety generated by the tournament algebras, in other words, the models of all the identities satisfied by the tournament algebras, so that's the same thing as, I mean, this we know basically by this is either by definition or Birkhoff's theorem, whatever. But can we find a short list so that we can just look at the models of that list? In other words, is there a short list of axioms so that the variety generated by the tournament algebras, that class that can either be created by homomorphic images of subalgebras of products, or the class that is all of the models of the identities satisfied by all tournament algebras, can we just think of those as the things that satisfy some small list of equations? Like maybe we're thinking, oh, we can just add like 2 or 3 equations into here in addition to these two, and anything that satisfies those equations, that will be one of the things in this variety generated by the tournament algebras. Like that's possible. Like that's conceivable, maybe. So what other identities do we have to add? Because there's some short list that will work. The answer is no. No finite choice of L will suffice. Or maybe I'll do an exclamation point. No. There is no finite list of identities that will make that true. There's no finite choice of L that will make that true. We also say in this case that the variety generated by tournament magmas is not finitely based. If there was a finite choice of L that worked, then we would say that it was finitely based. So this variety is not finitely based. There's no finite list of axioms that define it. But we know there is there is a list in the sense that you could just take the infinite list of all possible identities satisfied by all tournament magmas. But that's kind of a cheap answer. So maybe we can fix the question by asking, is there a nice... yes, we're all varieties are infinitely based. That's why we don't call it infinitely based. It's just kind of a trivial situation. Because of Birkhoff's theorem, you can always just take all of the identities satisfied by all of the algebras in the variety. So, amusingly, being finitely based is actually the special thing. Everything's infinitely based. Are you based as well? Okay, yeah, and I do make it so that you can make clips out of these videos when I post them on YouTube. Okay, so maybe I'll finish asking the question that I wanted to ask, and then I'll address this question about the discrete neural nets paper. Let me just finish asking this question first. Universal algebra is quite something, and there's lots of good jokes to be made about that property. Is there a nice infinite list of axioms L such that the same thing, the variety generated by the tournament algebras is the models, all the algebras that satisfy those axioms. And now nice means not the silly answer of just take all the identities that are true for all tournament algebras, because we don't know how to describe those in general. That's the problem. And so my paper doesn't answer that question, but it does potentially give a place to start for answering it. And the answer to this still isn't known, to my knowledge. In my paper, I end up showing that, basically I show that the variety generated by tournament algebras is actually the same thing as the variety generated by, maybe I'll just say S, for various special kinds of tournament magmas with more nice properties, more properties. And so there's many different special classes that you can use, but the reason why this might be progress is because then you can say, I don't need to answer this question for the variety. I don't need to think of it as being generated by all tournament algebras. I can just look for what is a nice list of identities that are satisfied by all of the special kinds that I described in my paper. And the special kinds are quite restricted, so it's possible that you can use them to understand the answer to the remaining part of this question, is can we find any equational basis, even if it's infinite, that we can describe nicely, and not just the cheap description of it's all the equations that are true for all the tournament magmas. So that's the question that I think could be answered using what I did in my paper, or at least that's a good place to start, but in the last 5 minutes I won't have time to answer it here. But I think it could probably be done. So there was a question about could I extend the paper on discrete neural nets and polymorphic learning, introducing spline functions as, I assume by adapting activations you mean the activation functions. Well, if you look, although there's the examples in the discrete neural nets paper, which is currently under review, but hopefully will be published in the not too distant future, well, the examples are mostly from polymorphisms of a certain kind of graph. The technique actually can be used in more generality, and so it is possible to replace replace these graph polymorphisms with polymorphisms of other things. So if your splines are polymorphisms of something, like maybe if they're, piecewise smooth or whatever, if they're some natural notion of morphism, say of the real numbers, if you think about that as an underlying object, then yeah, this general method would work as well, as long as they're closed under composition. Yeah, I mean, it is possible to use that as an example as well. I have another more abstract paper along the same lines coming out, hopefully, in the not too distant future. You can already see me talking about some of the ideas in some videos on YouTube. But so stay tuned for that as well. Are there any last questions or comments about anything to do with this universal algebra question or anything we talked about today at all? As always, I just want to say, I really appreciate everyone's interest, and everyone has really wonderful questions. If I was just trying to give a lecture just by myself, just to the screen, about these things, it wouldn't flow nearly as nicely as this does, because, and I'm glad I was able to record the chat too. It's gonna. I figured it out. You can watch with the chat too, and I really appreciate, again, just everyone's questions. This is maybe a more structured course can be helpful depending on what your goals are, but I think that this is a really great way to kind of get into things, see what's going on. This is also kind of more like how people actually learn math. As you get further along, you just start kind of hanging out with people and talking about things, and at some point maybe you say, oh, okay, I'll go read a book a little bit or something, but it's important to get the actual ideas, and you don't always get those by just reading the densest possible treatment. So actually I'm starting as a postdoc at, I just am finishing my first postdoc at the University of Denver. I'm starting my second postdoc, and hopefully my last one before a tenure track job, at CU Boulder in the fall, and I believe that they are going to have me teaching some amount of graduate algebra. I'm not sure if I'll be teaching a whole 2-semester graduate algebra course there, but I will be teaching abstract algebra, at least to undergrads and grad students. I should have at least a graduate topics course or something. Now, as far as doing that online, I'll have to see. Yeah, thanks. Yeah, it is exciting. As far as doing that online, I'll have to just see how things balance out, I do still kind of like teaching the old school way, especially because, I didn't get to start off that way because I started teaching during COVID. But yeah, I definitely will keep it in mind, and maybe at some point, at some point in the future, I will actually have, some graduate algebra lectures online. Who knows? But yeah, thanks again so much, everyone. I think I'm going to call it here. The chat will be able to pass an algebra qualifying exam. Yeah, absolutely. Well, it's been really awesome. Again, thanks so much. And stay tuned. Next week, I'll have something new. Don't know what yet, but I'll have something totally new, and I'm sure Dobby will be there too. Do you want to say bye, buddy? You want to say bye to everyone? Yeah. All right.
You're so cute.
Well, yeah. I'll see you all next time. Yeah, my dog. All right.